Hi, my name is Calvin Pierce, and welcome to my COMP3132 Machine Learning Assignment 2. So, in this assignment, we are working with our ever so familiar iris dataset, and we're looking into some problems that we might encounter while training and evaluating our model, such as overfitting and bottlenecks. With that being said, let's get into it, and I'll explain, and hopefully you can learn something as we go on. So the first thing that we actually do for our sake is we import our iris.csv file containing our dataset into our Google Drive, just so it's here every time, so we don't have to always drag and drop it into there. Otherwise, you will have to remember to do that at every session runtime, every time you load up Colab. But if you keep it into your drive, you can conveniently have it there. And with that, also solves our first question. First, we uploaded the iris into my Google Drive. We saved, then we found the path of our iris.csv file, saved it into a variable called file name, imported pandas, and read the file as such. So with that, I can show you our first 5 rows of the data frame using the .head. And if you actually wanted to, you could put a 5 inside of that .head as a parameter. I guess I will show you as an example right here. You could do something like that, and it'll give you the exact same answer, because if you don't specify that number, it'll always default to 5. Otherwise, say you wanted the first 3, you could just say 3 instead. But we'll leave that blank just for the sake of what I had already done, even though, once again, it does not technically matter. And as you can see, we have our little iris data set. I believe it contains 150 different rows or something. Don't quote me on that. I'm sorry, I should have learned that before I started the video, but we're going anyways. So we have the petal length, width, and the sepal length and width, as well as the species of flower. We have 3 different species. As you can see below, we have Setosa, versicolor, and virginica. So what we want to do is we want to convert them to integers so that our neural network can have an easier time reading and understanding those, because it just works better with numbers than it does strings. It's a little confusing for it. So what we're actually going to do is we're going to map each of those into a key value pair. So we got our key Setosa. We want that to be binded to 0, versicolor to 1, and virginica to 2. And then what we do is we look into our data frame iris. If you remember, I'll just scroll up. We actually stored our data frame inside of this iris variable right here. And so what we do is we look at the species column inside of our iris data frame, and we map our species map right here. So every time it sees Setosa inside of here, it'll say, hey, I know that to be 0, versicolor to be 1, and virginica to be 2. So if I show you the first 5 elements of our data set, once again, you can see our species, instead of being Setosa, if I just leave it right here, you can kind of see first one Setosa there, and instead it is now 0, as we have mapped out above. So, going on, what we're going to do is we're going to select the first 4 columns of our data frame. And so what that would be is it would be all the information, per se, for our data frame. And then what we do is we want to capture the last column, which would be the label for our data frame, which would be once our machine gets to look at the petal length and width and all that stuff, it can say, hey, this is 0 or Setosa. So we can see our first 4 columns, aka the information columns, are stored inside our variable x, and I just show you the first 5 rows just for mine and your sake. It's nice to have a visual for the data, at least I always think so. And then next we're going to store our labels, aka our last column, inside of our y variable, once again showing you our first 5 columns. Once again, you can see our species, 0 all around right there. Those are standing for Setosa. So continuing on, we're actually going to split our data into some training and some test data. And the way we're going to use that is, if you recall from our previous semester, learning all about scikit-learn, we're going to take scikit-learn and we're going to use one of their libraries, training test split, and it's going to make it a whole lot easier for us. So what we're going to do is we want to make 4 variables, xtrain, xtest, ytrain, and ytest. And what we want to do is we want to take that scikit-learn library, train test split, and we want to say, hey, this is our data that we're taking inside of our x. as you remember, which was the first 4 columns. And we want our labels, aka y, which was our last column, which contains 0, 1, or 2, being the labels for the flower species, such as Certosa. And then we have our test size. So we actually get to specify how much we want in our training size and our test size. This is actually a percentile. So we're splitting it into 80% training data and 20% testing data, and they get split into these variables over here. So that would be 80% of X, and that would be 20% of X would be the training, or 20% would be the test, rather, sorry, and 80% would be the training data. And we use random state 1, 2, 3 for this assignment, just so that we have our answers all looking kind of similar, just so that we know that we're all on the same page here. And so next, we're just going to show you the first 5 rows of all of those newly created variables, because once again, it's nice to have a visual for things. At least I think so. So we got our X training data, our X testing data. Once again, this is 80% of our original X data frame, and this is 20% of our original X data frame. Then we got our Y training, which once again is the labels. You can see 0, 1, and 2. Remember, we mapped them out earlier for the species. And our Y testing data. And then what we want to do is we want to make sure that we actually split up our training data as we wanted to into the 80% training, 20% testing. So we're just going to confirm our lengths right there. And as you can see, we have 120 for the training data and 30 for the test. We are all good to go, and we will continue on moving on. So next, what we're going to want to do is we're going to want to use some one-hot encoding. And so what that does is, instead of having 0, 1, or 2, it'll be kind of split up in either 0 or 1. 1 being the identifier, 0 being no. Kind of like you can look at it as a binary, kind of just being like yes or no. So, for example, what we'll do is we will import from our Keras library the toCategorical function. We could have defined it ourselves, but luckily Python likes to make our lives a whole lot easier. So we're going to go with one of their built-in libraries, toCategorical. And what we're going to do is we're going to actually store them inside of our own variables, one hot training labels and one hot test labels. So what we're going to do is we're going to say toCategorical, our Y training data and our Y testing data. And now we get to the actual machine learning part of our assignment. And this is when things get kind of, well, I don't want to say kind of, they get really cool, a little confusing, but I promise you it's worth it. This is where all the magic kind of takes place. So what we do is we start and we define our neural network. So what we do is we go from Keras, we want to import the models and the layers libraries, once again making our life a whole lot easier. And we're actually defining a sequential model that contains 3 layers. The first 2 layers have 100 neurons each, or hidden units, and they use the ReLU activation feature. And finally, for our last one, we only have 3 hidden units or neurons. That's because we only have the 3 labels, and you want that to match up with the actual output labels that you have. And our activation is softmax. Once again, just because that's a probability one, it gets to actually pick it. So what we do is we're going to compile our model, and we're using RMS prop, and we're using metric accuracy, and our loss function, we're actually going with categorical cross entropy because we are using the one hot encoding, and categorical cross entropy specifies, and it is its signature, I will say. It works best with one hot encoding. So next, we're going to fit our model, and we're going to use 20 epochs with a batch size of 10. So what we're going to do is we're going to take our X training data and our one hot training labels that we just encoded, and we're going to tell it to run through 20 epochs of our model defined up above, and batch sizes of 10. So I'll show you the whole thing. I'll just scroll down a little more here. Never mind, let me scroll up. So you can see our 20 epochs. You can see our loss score, our accuracy score, and I'll give you a second just to look at them. I will scroll back to it. I want to come back to it. I'm jumping too far out of myself if I explain it all right now. So what we're going to do is we're going to calculate the result, and we're evaluating it just to see how accurate our model works. So we're taking our test loss accuracy and our test accuracy, and we're evaluating it with our X testing data and our one hot testing labels. as you can see, our loss score is really good. Same with our accuracy, 96. We'll round up to 97 in this case. Very good. And now I'm going to show you a little bit of the fun of the neural networks and kind of what we can do in order to change our result and better fit or worse fit and see how it impacts our data. So what we do is we're going to take that same exact model, but instead of having our 100 hidden units or neurons, we're actually going to change it to 10. And so we still have the same amount of layers, and we still have our 3 outputs, because once again, we only have our 3 outputs. We just want them to match still. We're going to just put significantly less hidden units or neurons. And we're going to run it again. Once again, since we're still one hot encoding, we're doing categorical cross entropy. And we're going to fit our model one more time. This time we're only going to run it in 4 epochs instead of 20, which is just our cycles. As you can see here, our loss score is way higher and are actually significantly worse. And we'll calculate our result again. Once again, our loss score and accuracy significantly higher and worse. And that just comes down to what we actually have is we have an information bottleneck. Because we're losing out on our data because we do not have enough neurons or hidden units inside of our original layers up above here. As you can see, we only have 10. So we're actually losing rather some of that data. And once that data starts to get lost, we can never recover it. It's permanently lost. The neural network trains and it ends up training on worse data and it doesn't understand as much. Therefore, loss is way higher, accuracy way worse, as you can see. And I'll just answer some of the stuff that I learned from the assignment, and then I'm going to scroll right back up because I did promise you that. So what we can see is the number of neurons impacts the accuracy of our model greatly, because our loss accuracy got way higher, our accuracy was way lower, and once again, as I explained, it's the information bottleneck. You're permanently losing that data and there's no way to recover it. And then next, the layers also actually impact our accuracy by overfitting. When we have too many layers, instead of learning, rather, the neural network ends up memorizing, per se, and it actually becomes worse when you try and test it with new unseen data because it doesn't really know how to learn or process anymore. It says, hey, I only remember this. Instead of learning, I ended up memorizing what the best kind of route is to take, for example, and what the optimal weights are. And so we can find overfitting. This is why I wanted to promise you that I would scroll up. We find overfitting when our loss accuracy and data starts to stagnate, or even, which is just a fancy word for stop improving, or even gets worse. So if we scroll up here, you can take a look at our 20 epochs. I think it starts happening at epoch number 11. As you can see here, we have a pretty good loss score. Our accuracy is up at 96%, and we're not really improving after that. In fact, we're kind of getting a little worse. We actually do improve over here, but once again, that's just overfitting our model, and it's kind of just learning the optimal weights of what it should adjust each hidden layer into. And so it's really not doing that great. And so we'll scroll again. And now this is where I told you, I promised you it gets a lot of fun. It's down at the very bottom. We're actually just going to change everything and kind of have fun with our model. And so as you can see here, we got our original model. We got our 100 hidden layers, our 3 hidden units, and aka neurons, our 3 layers. As you can see here, we're still using RMS prop, categorical cross entropy. And what we're doing is we're just doing 4 epochs. So kind of what we did in question 9. Batch size, still 10. And we're just looking at our accuracy. And so as you can see, it does actually get significantly better than what we did earlier with the bottleneck and the 10. Apologies to scroll a little too far. And the 10 neurons, because we're not losing that data. So we can actually better fit our neural network, and we're doing a more optimal amount of epochs, because once you get more, you're starting to get into the overfitting, and really it's not that great. But as you can see, our accuracy score actually is pretty good. Our loss score, not that bad, and that is a pretty good neural network if I do say so myself. However, what fun would it be if it was perfect every time? So we added a couple more layers of 100 neurons because, well, if it worked so well above, a couple more layers would only help, right? Or so you would think. Once again, we're actually going to rocket to 20 epochs, which is what we had our original one through, so we might experience a little bit of overfitting. And as you can see, our accuracy actually gets really good really quickly. Because we're doing those layers, it actually is very minusculely changing those weights when it goes through it, and it actually becomes a problem. So you can see it gets really quickly, really good. You can see epoch 7 here, 94% accuracy, and then drops down to 88. It really stops kind of learning and starts getting into more of that memorization habit, something we want to try and avoid. And then I believe I only have this one last one here. As you can see, we got our sequential model again. Once again, we cut it down to our normal 3 layers, 100 neurons each in there, 3 for our output. That'll never change. And what we do is we have it with 20 epochs, but we change our batch size up to 100 instead of 10, just to kind of play around with it, see how it gets. You can see it actually gives a little warning. It did not like that, but that's okay. But it's taking a lot bigger data, and it's not really processing it as well. It gets good, epoch 6, you get a really good accuracy, but the loss score is really high, and it's really not dealing with the data well. I believe the batch size is too high, and that's what's affecting it. And so overall, I learned a lot of good things about this. I actually, before I exit, I want to tell you, so what I was actually struggling a little bit trying to do this assignment. If I scroll up, go to about question 6, we can see here we use our categorical cross entropy. But silly me, I actually, instead of fitting our one hot training labels, I was trying to fit our Y train by mistake, and I was figuring out why our categorical cross entropy couldn't work. And why it couldn't work is because the categorical cross entropy, as I said earlier, works great with the one hot encoding, but it doesn't work with the normal integer value, which is what we had our Y train data, because remember we changed the setosa to 0 and 1 and 2 for those labels respectively, and so on. And so overall, it was a fun assignment. We learned a lot about bottlenecks and overfitting. Not so much overfitting as we touched on that in assignment 1, but a lot of information bottlenecks and how neurons and different layer sizes can greatly affect the outcome of your machine learning neural network. And thank you for watching, and that concludes assignment 2.